Okay. Now, how do we ensure the structural integrity? For example, if you see here, we try to keep this internal ties. So, that helps us to, for example, location 1, that what you see here between the two elements, we try to put some internal ties that are going to connect the elements together. That will helps to take up the lateral forces from shear wall action. So, that means I need to have a elements or reinforcement that will come from the diaphragm and that will be attached to the shear wall. In addition to that, we also need to have peripheral ties that is going to help in ensuring the diaphragm action. So, these are all typically happens at the corner region. I need to ensure that again some tie element that should connect at the elements that are joining in these corners. Now, floor to wall ties. Now, this is going to help in taking up the horizontal force from anchorage of the floors to their support. So, for example, we are looking at the third location. Now, again the floor reinforcement also should be tied into the walls, shear walls that are there. So, that is what we are saying. This is your third. So, these are the multiple. By providing this connecting reinforcements, we are going to ensure a very good structural integrity, so that all the elements will act as a one unit and it will help to transfer the lateral loads. In addition to that, we need to also have vertical ties, for example, between the two elements to ensure that cantilever action of the shear walls will always be there, right. So, the vertical tie elements also should be ensured and designed properly. Now, what are the critical joints? Now, let us look at what are the critical joints that you have. For example, you see here, if a precast for example, precast slab, if it is directly kept on the column, right. So, what can happen is there is a possibility that your reaction, if it is right at the center, it has to be here. Now, if this is moving for some reason, the slab is moving, then what will happen? Your reaction point will shift like this, then you will have localized crushing of the concrete on the column element. So, this is directly resting the precast element on this type of column is not advisable. So, typically you need to put some kind of a bearing pad, so that even if a small rotation that it is happening, the reaction location is not going to change much. This is only going to be small shift, so and that will not create this kind of a localized spalling that it is possible because of the rotation of the slab element. So, bearing pad is important to put it at the critical support locations. Now, the next one is basically, if you see here, again when a beam element is put directly on this column element and it is going to apply a lot of load in this region, then if you do not have any confining reinforcement like this, then it is going to develop these kind of a vertical splitting cracks, just like we had looked at it in the post tension deep beam. In the anchorage zones, you develop these kind of a busting crack. So, similarly, when you have a huge concentrated load that it is coming, the end regions, if they are not confined, then you will have problems because of this. So, it is always better at the ends of this critical elements to provide adequate number of your confinement links, then you will avoid this kind of cracking. The next case is the connection between beam and column. Typically, we do not want to have simply supported elements, slabs simply supported on a column, for example. If the column, due to some reasons, due to soil condition, if it is undergoing settlement, then what will happen? There is a possible failure that can happen. The element can dislodge and then it can fall off. So, to avoid that, typically what we do is, this is what we said, you have this kind of a looping mechanism that it can, we can do that, right. So, you have reinforcement that is coming like this, reinforcement that is coming like this, and then you put this and then you add this cast in place concrete. So, you have two protruding hairpin reinforcement and they can be connected together by some horizontal reinforcement, and this region can be done using cast in place concrete. So, this way a simple connection can help. Even if there is a settlement, it will not let the slab element or a beam element to fall off. So, that is another important thing. The next one is a dowel or bolt in a pinned connection. So, we talked about this. So, usually it is better to provide some kind of a dowel even though it is simply supported, the dowel will help in case if there is any loss of bearing, so that the element is not going to fall off. So either you achieve this kind of a connection or achieve through a dowel connection, so that in case of any untoward movement of the vertical element, the horizontal element will not fall off. So that is the idea. Now, what are the seismic aspects of connections in precast construction? Now you see why precast are not widely used in seismic regions. In the past, there were a lot of failures that were observed because of the poor performance in the past, and at that time we are talking about 90s and 2000, lack of proven design methodology, they were not available, and lack of also full scale experimental validation of different types of connections, and mostly the columns were assumed to be pinned at the top, and they are also not very cost effective. Now this is one of the classical example of a parking garage that failed in California State University Northridge during a 1994 Northridge earthquake. And you see this, the entire garage was of precast post tension construction. It was built in 1991. In fact, due to the vertical ground motions, the center columns they crushed. Because the center columns crushed, it took all the perimeter element into extreme bending of external columns that you can see here. So this is the reason why, because the central element, if it is crushed and it has fallen off, then it is going to basically pull all the perimeter frames towards it, right? So that is the kind of failure happened. So but however, a similar shear wall type, this is a framed construction, and you can see, but however, a similar shear wall post tension parking structure that was built in 1991 was undamaged during the same earthquake. So that tells that if you design the system properly during an earthquake, you can prevent failure. So it is all about proper design and detailing. Most importantly, the detailing has to be done properly. Joints and connections have to be done properly. Is very important. Now, what are the objectives of seismic performance from precast point of view? We want to have a damped response. So what is the meaning of damped response? We want the system to dissipate the energy, because earthquake, when it is coming, it is going to input a lot of energy into the building system, and the structural system should be able to dissipate that energy. So the structural system, whatever we are adopting, it should exhibit a damped response. So whatever that additional damping that we can achieve, that is going to limit the peak drift during a seismic. So what is the meaning of drift? Drift is nothing but lateral displacement divided by the height of the story, and we need to limit that drift. And the structural system also should have minimal damage even in a strong earthquake. That means typically we accept some damages in earthquake design, but the system should only undergo minimal damage even in a strong earthquake. That will help in quickly we can reoccupy, and even after an earthquake. For example, if you have a hospital building or an important bridge, I don't want to have damage, and if you are not able to utilize the structure, then we will have problems, right? So we also want to design a system in such a way that it will have only minimal damage after a strong earthquake. The next one is a zero residual drift. That means after an earthquake, the frame should revert back to the vertical alignment after an earthquake. That means it should go back to its original position. So this is also called as recentering. That means after an earthquake, it should go back to its original position. So these are the three important phenomena. We need to have damped response. After an earthquake, we need to have minimal damage, and the system should also not have high residual drift. That means it should go back to its original position. Now, what are the possible configurations of precast frame system? We can have continuous beams with the discontinuous columns, or I can have a continuous columns with discontinuous beams, right? So let's look at it. So for example, I have here is a continuous beams with discontinuous columns. So what is the meaning of that? So you see here, the beam is a one single element which goes from one end to another. But however, if you look at the columns, they are all discontinuous. These are single element and they are connected together. So, with this approach, if you see here also, when we go for this continuous beam system, typically what we will do is we try to use an unbonded tendon, and then only at the ends we bond it. Only at the ends we tend to bond it. So, if I have to adopt this system, usually end up with long heavy beams, and here columns must be accurately placed for bars to fit, because I want to have continuity of the bars going through that, right. So, the holes have to correctly match so that the dowel bars can go inside, and then I can do the grouting to ensure that there is a continuity between the vertical elements, column elements. Now, there is another concept which is a continuous columns with the discontinuous beams. So, what you see here, you see the blue color element, this is a single element, right, and beams are all discontinuous. So, this is commonly adopted in precast construction. Okay. You see here again you have pre-stressing tendons that are there running from one end of the building to another end of the building from on the beams. Then you also have some normal reinforcement that it is kept. You see, these are your normal reinforcement, your rebars. So, you also keep some rebars. Okay. Right. So, this is one system. Now, what are the possible configurations of reinforcement? I can have everything with only unbonded pre-stressing steel. It will be easy to construct, because again advantages of pre-stressing reinforcement we have said, because they are flexible, I can roll it to any length what I want. So, I can do the post tensioning of the entire building from one end to another end, right. So, it is easy to construct, but however it is not having hysteretic damping. So, it cannot dissipate the energy, right. So, additional damping can be provided through external devices or by incorporating RC frames in parallel with unbonded PT frames. So, I can have some frames which are made of only PT and some frames which are made of RC. During an earthquake, there are RC frames that will undergo energy dissipation, but however the PT frames, they will not dissipate the energy, right. They will remain elastic. Now, I can also have unbonded pre-stressing plus rebar, which we call that as a hybrid frame, and these are all lot of pioneering work that happened from the program PRESS program, pre-stressed seismically safe system, and Professor Priestley and his group at University of California, San Diego, they have done full scale testing and lot of improvements have been suggested. This report gives you a lot of useful information, more detail you can look at it. The idea here is to just illustrate the concept, right. So, the reinforcing bars here, it helps in contributing to the internal hysteretic damping, and at the same time unbonded PT system will help in, this helps in recentering or zero drift. This helps in energy dissipation, or we should say damping. Okay. So, I achieve zero drift or near zero drift. Through rebar, I also dissipate the energy. So, that is why the hybrid frame gives you both options. So, now let us look at it. If I have only unbonded pre-stressing tendon like this, right. So, and what I do is I run across the PT beams. These are individual elements. This is one element, this is two element, and they are connected through a PT cable, which is basically like a rubber band. So, I stretch it and I connect all of them together, and then at these joints basically you grout it, right. Now, the next system is, in addition to this unbonded PT tendon, I also put some bonded rebar only at these regions. These are locally debonded, okay, locally debonded, okay, these are locally debonded, okay. So, why we do this debonding is basically to localize the damage in the rebar. Say for example, after an earthquake also, if this region is damaged, then I can quickly go ahead and access this location and repair it, and then use the same building after earthquake. So, that is the idea, right. So, now what is it? For example, if you look at only the PT system, you see here during an earthquake action, this is the kind of hysteretic response that what we are going to get. And if you look at it, the area within this hysteretic curve, it gives you how much energy is getting dissipated. For the system one with only PT tendons, you see here, but one advantage is after an earthquake, there is no residual drift. That means you achieve recentering. That means it can go back to its original position. And the behavior is non-linear elastic, and you don't get much energy dissipation. There is a very low damping. But if you look at only system with the rebar only, you see here the lot of residual drift. You see these gaps are there. Right? The column is not at center, so this is what we said, drift, high drift. But however, if you look at the energy, the area is very high. So that means I am having high damping and the behavior is non-linear inelastic. Now I want to have benefits of both. From the PT cable, I want to have recentering. From the rebar, I want to achieve the high damping or energy dissipation. So that's why the hybrid systems are quite attractive. For example, in a typical moment resisting frame, the column like this here, it undergoes a double curvature, and we know that I am going to have cracking and crushing that it is happening. So it's basically the column is in a bending mode. You have tension cracking and crushing of concrete in compression. So the moment you have tension cracking and crushing, you see that lot of damages are going to happen to the column element. Now what we are saying from here in the second approach is you have a rocking mode, right? So here in this case I am showing it for a column, but typically here in the other next case your beams are going to have rocking mode. So you see here the column, they do not undergo any curvature, so there is no damage, right? And you have only concentrated rotation here, and only at the localized regions like this I am having high contact stresses that will lead to some localized damage that can be actually quickly repaired after an earthquake. So in hybrid combinations, if you see here, I can also look at now we look at only with PT what happens and only with rebar what happens. Now I can have different combinations. For example, with only in PT and zero rebar, then I get this kind of a hysteretic response. The next case, I have PT 75%, rebar 25%, then I get some energy dissipation, but at the same time, it may not be adequate, right? So now PT and rebar 50-50 when I put it, this is the kind of energy dissipation that I will have, or hysteretic curve that I will have. And PT and rebar, if I have PT low and rebar high, you get very high amount of energy dissipation, but you will have high drift. So that means a lot of residual deformation that will be there and drifts will be high. So in this system. Now only rebar, of course you get 100%, without PT. This is the best from damping point of view, but however from recentering and less drift point of view, this is not a good solution. So we have to choose the combinations and then design for it. Now what is the deformed shape of a hybrid frame component? Again, these are the schematic that are taken from this press report, and you see here the deformations are happening only in these regions at the joint. Now the column is also going back and forth, and it is not going to, columns also can be post tension, typically that's also done, and you will have rocking mechanism that are happening in the columns as well. So you get this kind of a failure, but you see here only at the interfaces the deformations are localized, and the damages are also going to be localized only at that interface region. Now this is a typical internal reinforcement layout for a hybrid frame component. You see here I have this green color elements are basically your PT tendons. They are the one that goes and connects all the beams together in a building frame, and these are your sleeves to connect the two columns. We say that column is going to be continuous, right? So and you can have the splices and sleeves for the column bar. They can be grouted as again, and only if you see here pre-tensioned strands are crossing that interface. Here in this system, no rebar is crossing that joint region, right? So this is system one. first system, only PT strands are crossing. And then the next system is you have combinations. You see here the red color, these are mild steel or your rebars. They also cross the joint region, and the green color, which is PT strand, they also cross the joint region, right? Now this PT tension ducts are typically they are ungrouted, and the joint regions are actually grouted with some fiber reinforced material, fiber reinforced concrete. And you see here typically the holes are provided in the columns so that this green color things can go, and similarly the red color element also can go through the joint. So in the columns, when you fabricate itself, the holes have to be designed so that your PT cable and this normal rebar, mild steel rebar, can go through the joint. Now as we discussed, if you see here, there's a yellow color region which is basically an unbonded region. So only at the edge the rebars will not be bonded, they will be debonded so that you can localize the damage on the rebar, right? So this is again internal reinforcement details for a typical hybrid frame that is used in a building frame. Now what is the design procedure? Again, the design procedure is same as we do for a typical moment resting frame. You have a rational design procedure, you do the analysis and you get your internal forces, and the design forces are going to be nearly same as that of what you get for your concrete special moment resting frame, and we can have an explicit evaluation of a drift capacity, and other parts of the frame can be designed as per the code. Now what are the assumption that we are making in your analysis and design? All the deformations are going to occur only at the interface, not in the beam, and PT is unbonded throughout the entire length of the frame, and it is only bonded at the end regions so that some connectivity is there, right? And otherwise most part of the beams it is going to be unbonded, and the CG of the PT tendon is assumed to be at the mid beam height. Now limit states, when we design for it, we check for two important limit states. Nominal moment strength, it corresponds to the design moment, and we use to size the reinforcement at the interface, how much the rebar should go and how much should be the PT cable that should go through the the beams. And for maximum probable strength, it corresponds to the maximum credible earthquake, the worst case scenario, and it forms the basis for capacity based design procedures based on the design, the forces that are coming in the adjacent element. Because you are localizing the failure only at the interfaces, we need to make sure that at other locations the demands are lesser than their capacity. So this forms the comes from the capacity design principles. Okay, so now how do you calculate your nominal strength? Now nominal strength is typically calculated based on the two conditions. Either it is smaller of corresponding to onset of strain hardening in mild steel, right? That what is the meaning of onset of strain hardening? It could be basically we define the yield as, let's say, 0.2% of your proof strain. That strain limit can be kept as one of the limit state. Then the next one could be the yield of the PT steel, right? This is actually comparable to how we calculate the strength for a reinforced concrete frame, which is similar to what we do for your reinforced concrete frame. Now what is the maximum probable strength limit state? Again, here we if you look at your rebar, so you get this curve and then you go like this, right? So the first case that what we look at here is, this is your stress and this is your strain, and we say the onset of your strain is 0.2%. So basically we 0.2% we take. So this is your yield, right? Fy, right? So 0.2% proof strain. Okay. This is your first condition, right? Now how about the second one? The second one is basically this, the maximum strain. So this is your second, this is your first. That's what. The second is the smaller of, again, the yielding other. For PT steel we don't want to, because we want that PT tendon to be elastic. It's a very high strength material. So the PT we don't want them to yield. So the maximum probable strength or nominal strength, you always take the smaller of these two strain conditions. And also when we design it in such a way that the system should have at least 3.5% drift capacity at the maximum probable strength. That means the system should be able to go at least 3.5% drift when it is subjected to maximum considered earthquake or MCE, and you should be able to achieve, the system should be able to achieve 3.5% of your drift capacity. It should not fail at 3.5% drift. That's what it is, right? So we can conclude based on that. So the idea of this particular chapter was to give you overview of different connections and how seismic designs are done. And we can say pre-stressed concrete can be designed to resist earthquake, particularly pre-stressed concrete or precast elements can be designed to resist earthquake forces. The important factor is in detailing. The detailing is most important. The connections have to be really detailed well, and the design of connections have to be really done in a careful way. The type of connection also what we choose, it plays a very important role. And recent advancements in connections like jointed ductile connection, they are very cost effective, and they also retain all the advantages of pre-stressed concrete. So with this, I think we can really design a structure that is seismically resilient as well. Okay, see, these are some of the references. If you want more information, a lot of work has happened in the last 20-25 years. PRESS program, I think this should be one more is from University of California, San Diego, they have done a lot of full-scale testing, and a lot of research reports are available. You can go to the reports and look at more information. There is also a YouTube video that gives you a full idea of precast hybrid moment frame testing, so you can watch it at your convenience, right? So with this, let's summarize what we have discussed. In this lecture, we've explored the basic force transfer mechanisms in structural connections. We talked about encasing and shear friction, and through double action and bond, all those things, how it is helping in transferring the forces we discussed. We also examined different types of connections in precast construction. So between column to column, slab to column, beam to column, and then wall to wall, all these connections that we discussed, mechanical, welded, bolted, grouted connections, and their role in ensuring structural integrity. And we also developed an understanding of how unbonded PT cables can be used for designing connections which are seismically resilient, right? So with this, we are ending this chapter. So thank you for your attention. So we'll continue in the next module. Thank you.